show up in the recording. The camera doesn't, but like I'll just hold my phone up to it. I've got this radar map app, and yeah, it looks like the shape of this thing is looks a lot like Thailand or Vietnam, just kind of flipped the other direction. I mean, just the shape of the clouds, but the north, like by Superior, looks like it's getting hit real bad. The whole state is going to get hit at some point. Like, Madison and Appleton and Milwaukee and so on are not part of this, but like this cloud's a moving, and everyone's going to see some rain today. But yeah, it's kind of. I hope it doesn't cut out here, and if it does, I'm sorry. We'll just. Okay, I should put this away. Clouds are mesmerizing. Let's. Um, yeah, hope you're doing all right. Um, Yesterday I was having some trouble with the stylus, and so I have a different stylus. I forgot that Dr. Allen had ordered me a backup stylus, but I'm still getting used to it. So I hope I figure out. I did okay this morning with just a couple hiccups, so please forgive me if I sort of write incorrectly. I'm gonna try to figure it out. My handwriting might look a little different. That probably bothers me more than it bothers you. Okay, all right, whew. And here we go. All right, so welcome back. Um, the key announcements. Quiz is open. Please do that. Today is ideal, but tomorrow is fine. There's a response. There's the pre-exam assignment. A homework that's due Thursday, and exam 3 will be available starting Thursday and due on Monday. So let's just dig into things. So we saw this definition last time. So let S be a finite set. Then an element P belonging to S raised to the cardinality of S, right? So this is a tuple, and how many coordinates are in there? It's cardinality of S. That's how many things are in there. So this is a permutation if all coordinates of P are different, and an element. Um, oh, okay. All right, let's try this again. I'm sorry. Oh my goodness, please don't laugh at me. My hand just cramped. Oh dear. You know you're out of shape when your hand is cramping from using a new stylus. Oh jeez. Ow. Okay. Ah. All right, fight through the pain. Okay. Oh my goodness. So, sorry. Oh jeez. Oh, that's painful. Okay. All right. Here we go. An element P in S to the R is an R permutation if all coordinates of P are different. All right. Slightly different example than yesterday. I have I just picked for today the set consisting of 4, 5, 6, 7, 8. Okay, so there's 5 things in S, right? Cardinality of S is 5. And if we looked at this 5 tuple, so 4, 6, 7, 5, 8, right? The parentheses are being used here to match this definition. We had a second definition yesterday, but I just want to stick to this one because it's a little more connected to the things we've done. So this element of S5 is a permutation. And we could also mention that this is a 5 permutation. If you had 6, 4, this is an element of S2, so this is a 2 permutation. And then the key thing I want to talk about is 4, comma 6. This is an S2. All coordinates are different, right? 4 and 6 are different. And this is a different 2 permutation. Okay, the thing that we didn't get to yesterday, I thought we would get to this, is that if you start with a finite set again, let S be finite, it's not in today's notes, but it's in yesterday's notes. I just want to mention that an unordered, so we looked at ordered, but now an unordered list of R elements is an R combination. So this is the nicer sort of like informal definition. But again, the issue is like unordered list. Like, what does that even mean? What does a list mean here? So instead of doing that, like this definition is fine and all, but it's going to help us out if we. So let me do that much scrolling. If we look at a definition that's kind of as formal as what we have up here for permutation, the idea being let's connect it into things that we've talked about, and just even if it's a little more technical, the fact that it's connected to things we've done helps make it make a little more sense. So if S is a finite set, then an R combination of S is a subset of S of cardinality R. Okay, so you start with a set, look at a subset. How many things are in that subset? Hopefully R things. So as an example, and I want to keep the example we see up here for permutation in mind, but I'll use the same set S, so 4, 5, 6, 7, 8. And now let's look at the way this one's defined, though. We've got here, it says subset, so we need to have a subset. So 6, 4, right? This is a 2 combination. And then if you look at 4, 6, I'm trying to make this match what we have over here as much as possible. This is the same 2 combination. I hope this clarifies the distinction here, right? Like when we write using parentheses, like up here, that's an ordered, right? Ordered pair. And then using the curly braces, what we have down here, these are sets. And so these really are the same set, aren't they? 6, 4, 4, 6, because in sets the order doesn't matter. So there's R combinations and R permutations. In R permutations up here, we have 2 different ones, right? 6, 4, and 4, 6. And then here, 6, 4, 4, 6, they're sets. And so they're the same set. So I guess what I want to ask is let's just fix a set S of cardinality n. Let's also just fix for now. So n is fixed, and then fix R. Oh, why do we need S to be finite? In principle, you don't. So I'm sure out there are definitions of R combination and R permutation with an infinite set S, but it doesn't really help for our purposes because we're about to do some counting problems, and it helps just to keep everything finite for us. So sorry for those listening to the recording later, you don't actually see the written question, so I should just state it. Why does S need to be finite? You could probably make versions of these definitions where S is infinite, but we're going to count things. And in fact, like yesterday, we started talking about like how many permutations are there, but even the number of R permutations, it would be infinite if S was infinite. So to keep everything finite so that we have counting problems and we don't need to answer infinity as the answer to a counting problem, we keep S finite. What I would like to do, though, is compare this permutations and combinations business, R permutations and R combinations. So let's fix a set S of cardinality n, finite set S, fix a number R that's less than or equal to n, then ask, are there more R permutations of S or more R combinations of S? What do you think? Let's ask the crowd. What do y'all think? You can all type an answer. Someone can unmute and say something, and feel free to provide a reason or not, but think about your own reason at minimum. Do you think if you fix a set S of cardinality n, and you fix an R, should there be more R permutations or more R combinations? What do you think? Right, there would be more R permutations, right? So getting kind of multiple responses of this. Yeah, and the point to the because order does not matter. Well, so in permutations order matters, but in combinations order doesn't matter. And when order doesn't matter, you don't get as many of them, right? So we expect there should be more R permutations. Okay. Right. So there's more R permutations. And let's then kind of look at least real brief what was the number of the right. So the number of each of these. So the number of R permutations of the set S with the cardinality of S equal to n is P of nr will be our notation for this, and it's n times n minus 1 times n minus 2 times, and keep going like this until you actually get to n minus r plus 1, and this you can actually write very conveniently and compactly as n factorial over n minus r factorial. Okay, so just as far as what a short proof of this looks like, we looked at a slightly more extended version of it yesterday. The point is that there's n choices for the first coordinate, and then there's n minus 1 choices for the second coordinate, and on it goes. So there's the n, there's your n minus 1, and in total, if you have a total of r factors, because there's r coordinates, then it turns out if you start with n minus 0, then your last one has to be n minus r plus 1. But again, so I don't want to belabor exactly how all of that is done. You can look at yesterday for that. What I want to do is point out some, and I should have done this in previous semesters, but I want to point out specific numbers in specific computations that I think are actually going to be helpful. So how many 5 permutations are there when you have a set of cardinality 5 to start with? Well, following the formula, you should have 5 factorial over 5 minus 5 factorial. So you have 5 factorial over 0 factorial. 0 factorial is defined to be 1, so you end up with 5 factorial, which is, I believe, 120. So just as a comment, one of those 120 permutations, just assuming that, let's just say S is the set 1, 2, 3, 4, 5, then one of those 120 permutations is 1, 3, 5, 2, 4. Right? And the point is, this is not just something special for 5. I hope you see kind of more generally, if you start with a set of cardinality n and you're looking at n permutations, there's going to be n factorial of them overall. I wanted to pick another example here, so let's look at the example of start with a set of cardinality 5 and then look at the number of how many 2 permutations are there. The formula should grant us 5 factorial over 5 minus 2 factorial. In other words, 5 factorial over 3 factorial, and this is 5 times 4 times 3 times 2 times 1, 3 times 2 times 1. Most of these things cancel. You're left with 5 times 4, that is 20. In fact, we can write out the 20 2 permutations, right? So here are the 20 2 permutations of the set 1, 2, 3, 4, 5. So start with, this set of cardinal, and here they are, right? So I'm just going to be very methodical about it and write the 2 permutations where the first entry is a 1. So you have 1, 2, you have 1, 3, you have 1, 4, and you have 1, 5. And then I'm going to write out the ones where the first entry is a 2, just to be methodical and go in order. 2, 1, 2, 2 doesn't count. Remember, all the coordinates have to be different. So 2, 3, 2, 4, 2, 5, and then the ones that start with 3, so 3, 1, 3, 2, 3, 3 doesn't count, so 3, 4, 3, 5, 4, 1, 4, 2, 4, 3, 4, 5, because 4, 4 doesn't count, and then the ones that start with 5, so 5, 1, 5, 2, 5, 3, and 5, 4. So these are all 20 of them. Now, so I just do that for the concreteness of it. I hope I didn't make a mistake. I hope you can't find one more. I hope I didn't repeat. I don't think I did. I was trying to be very methodical. Just put them in kind of order. But now the question I want to address is, well, how many two combinations? So we just dealt with two permutations, but how many two combinations of same set, 1, 2, 3, 4, 5, are there? Or, I mean, I don't want to just answer this question alone. I want to use this one example to talk about the more general situation of how do the number of R combinations and the number of R permutations, how are they related to each other? So I think, yeah, this one question is concrete, but more importantly, I don't want to just write them out. I want to think about, like, how is this question that was just asked, how is this related to the number of two permutations, which we just thankfully, fortunately, have right up here, right? There's all 20 of them right there. So let's think about how we can relate these numbers, right? We have this theorem that was reviewed from yesterday of the number of permutations, R permutations. But let's, even in this tiny example, right? Let's think about how, like, for instance, ordered pair 5, 3, ordered pair 3, 5. These are different two permutations, two perms. But then if we just keep these order of things, set 5, 3 and set 3, 5, these are the same two combination, right? So think about, like, keeping these orders here in the same number just to be able to count what's going on. You see how we already said that there's more two permutations than there are two combinations. Right? Everybody who responded said more R permutations in the chat, but let's think of by how many more. And in this case, it's overcount, like the number of permutations versus the number of combinations, right? This is by a factor of 2 more, right? So there are more two permutations by a factor of 2, right? Because both of these two different two permutations kind of collapse down to it being just a single 2 combination. Does that work for everyone? I'll just maybe pause for a moment, make sure we're okay with that, because that'll lead into the next question. The natural question is not just about 2 permutations. Are we okay with that? Finger's still kind of cramped. I'm just, like, writing through the pain. Okay. Should stretch. Well, maybe okay. All right. Well, then let's think about something a little more generally, right? So more generally, how can we use the number of R permutations to get the number of R combinations? So just as a more general thing, and to address an answer to this question, to discuss it, I think it's helpful to still look at a concrete example again. Okay, so what I'm going to do is I would like to look at, as my notes have, like these, I'd like to look at these 3 permutations. So 3 dash permutations, not 3 of them, okay, but 3 dash permutations of same set we've been working with here, 1, 2, 3, 4, 5. I needed up to 5 just to, like, there needed to be enough to, like, be able to see what's going on. So here are the 3 permutations of 5 I want to talk about right now. So there's ordered triple 1, 2, 3. There's ordered triple 1, 3, 2. There's ordered triple 2, 1, 3. Notice I keep using the same 3 numbers. 2, 3, 1, and then 3, 1, 2, and then 3, 2, 1. These are, I believe, all of the 3 permutations of this set, let me call this set S. These are all the 3 permutations which use the numbers 1, 2, and 3. But these all collapse when going from the 3 permutation story to the 3 combination story. These all collapse to one 3 combination, right? Namely that 3 combination, well, read as a set, and then the order doesn't matter, but I'll just keep them in numerical order here just to present it. So in case you were thinking from the work up here that the factor is always just whatever r is, you see how it's different here? Like, do you see how there's now 6 of these, right? 6 different 3 permutations all end up making the same 3 combination. So where do we get the 6 from? Where do we get this 6 from? If you were expecting a factor of 3 and you see this factor of 6. 3 factorial, right? 3! Sorry, I had to, at least once a semester you have to make that factorial joke, as terrible as it is. So yeah, 3. So by factorial, so what's going on here? This is by a factor of 3 factorial, right? 3 factorial is 3 times 2 times 1, which is 6. And I want you to actually see it. It's not just a number to just notice, but you'll notice 3 factorial is, take a look there, what's in the blue box here, those are the, if you just had the set 1, 2, 3, those are all of the 3 permutations of a set of cardinality 3. And that goes back to, that's the reason why, if I scroll up, sorry, that's why I wanted to work out this here, that P of n comma n is n factorial. That's, if you look at the full the permutations of size being the cardinality of the set, that's n factorial. So in general, this keeps holding, right? So there are, oh, that's a little error in my notes. There are more R permutations. In my notes it says combinations, sorry, but more R permutations by a factor of R factorial, right? When you compare the number of combinations versus the number of permutations, how do you go from the number of combinations to the number of permutations? Well, the number of combinations is smaller, you always have to multiply by R factorial. So this leads to this overall thing, right? The number of R combinations of a set with n elements. So you start with a set with n elements, and then how many R combinations are there? This is, well, notation-wise, maybe not too surprising that we would use CNR. Earlier we just used PNR for permutations. So first of all, let me present the theorem. N factorial over n minus r quantity factorial, r factorial, both of those things in the denominator. The proof of this should be super short here, right? That C of nr, like this thing representing the number of combinations, this should be, start with PNR from earlier, divided by r factorial, right? Because that was the discussion here, right? This line down here, that's what's going on. So that we'll just call it with that. Is that working for everybody? This is maybe a good place to just pause and make sure. We talked about how many R permutations there are yesterday. We can see that the number of R permutations should be larger than the number of R combinations by a factor of R factorial. So we just need to divide by, the point is right here, maybe circled in blue, that portion is the formula for the number of R permutations. So we needed to divide by R factorial. Okay, just in terms of some notation, in addition to the C and R notation, you'll also see this notation. So it looks like a fraction n over r, but the fraction bar is missing. We surround this in parentheses. So this is called n choose r. That's how you say this aloud. I should also just have you note that applying this new notation, n choose r ends up being the same number as n choose n minus r. So take a look at back up here at the formula. So right, this is n choose r after all. This big fraction. Sorry for the blue circling. I probably shouldn't have done that. But if you plug in n minus r for r, you end up with the same number in the end. So it's just a kind of a funky feature of this thing. We already, in a sense, have talked about this number, but I want to just talk about the language. Why is this called n choose r? In part, it's called this because n choose r is the number of ways to choose r elements or r things out of a total of n things, n elements. So it's called n choose r because you have start with n things. There are n things that you can pick amongst, and you have to select r of them. So out of n things, choose r. So n choose r. That's where this language comes from. Just to clarify, I mean, we've actually, I know this discussion, I want this to connect back and forth. Like sometimes the language is situational about choosing things. Sometimes the language is much more in set language, but I want to connect those things together. So let's like make sure that this phrasing here makes sense via example. So let's just say question, 5 people are competing for a prize. And let's just say that 2 people will be co-winners. So there isn't a first place and a second place. It's just like there's going to be a tie for first place. It's just how this game is, right? 2 people are going to win. There's no first and second place separate. It's just 2 people will win the same amount of money or whatever, right? So they're 2, it doesn't matter. First place versus second place is just 2 winners. And then how many ways can the contest end? So what I want to do, and this is the kind of thing I want you to be thinking of all the time, but I want to model this by spelling out some details. So sorry if you're like, oh, we're really writing this out right now. But each way the contest ends, I'm going to say that this corresponds to. This is all very hazy. This doesn't feel very as let's say robust or I mean there's detail here, but it doesn't feel as formal as some of the stuff we've done earlier because we're trying to connect this situational stuff for which we don't have a lot of formal language at all to very formal things that we have done. And I want to say that this should correspond to a subset of the set. Let's just go with the set 1, 2, 3, 4, 5. But not just any subset, a subset of cardinality 2, right? So what I'm trying to do is I want you to think of the set. I know it's just a set of 5 integers, but I want you to think of this set as being like a set of 5 people. And just the first person is named 1 and the second person is named 2. And so the way the contest ends, if there's 2 people who are co-winners, that should whoever, like if it's like here's an example. Let's just say that it's contestant 3 wins and contestant 5 wins. So those are the 2 winners, because contestant 3 and contestant 5. So my example here I'm trying to get at is the set 3, 5. That's a set of cardinality 2. And those are the 2 winners, contestant number 3 and contestant number 5. Right? That's and so then here's I hope that works, but writing out like this takes up so much space and writing this doesn't. as sort of our little kind of in-house notation for this. But then we can write out all the ways the contest ends by writing in set notation instead. So I'll be very methodical about it. So all of the subsets of the set 1, 2, 3, 4, 5 of cardinality 2. So there's 1, 2, 1, 3, there's 1, 4, there's 1, 5, there's 2, 3, there's 2, 4, there's 2, 5, there's 3, 4, there's 3, 5, and there's 4, 5. And that's it. So as far as the subsets of 1, 2, 3, 4, 5 of cardinality 2, here they are. There's all 10 of them, right? And if you work it out, you could do this by formula too. So whether you do C of 5, 2, or you write it as 5 choose 2 like this, you end up with 5 factorial over, well, 2 factorial times 3 factorial, and this ends up being 10. Just as we did some notes a moment ago, I want to, like with, we saw that number n factorial appear. So I just want to point out what n choose 1 is. So you can run it through the formula, something that looks like this, but once you compute this all down, you're going to get n. So the reason is because, and actually I'll provide that reason right now, because, and I'm going to give you 2 reasons, 2 different ways to view the answer to this question. First, n choose 1 following the formula is n factorial over 1 factorial times n minus 1 factorial. And now if you write this n factorial out, isn't it n times n minus 1 factorial? Very common Calc 2 style technique. How do you do n choose r in LaTeX? I knew somebody was going to ask this at some point. So it's actually in my notes literally right after next thing, but I'll just say it right now. So if you have the AMS math package as and you probably do up at the top, \binom, and then there's n choose k. I guess you asked for n choose r, but you get, yeah, okay, so like that. And so then why binom? That's coming up in just a moment. So binom, right? But yeah. So that's why I've held off until now. But yeah, thanks for the question. At least there's an answer to your question. So here, 1 factorial is just 1, but then you have n minus 1 factorial. You get a lot of cancellations here, right? So you're left with, after those cancellations, n factorial. So there's nope, not n factorial, just n, right? Because just that n. Okay. So there's an algebraic answer to why n choose 1 is n, but I want to give you another answer to this question. And I think it's helpful to think of this both ways. I mean, this is the whole point of this section, is think about it like how many ways to choose one thing out of n things. Well, there's n ways, right? Like the point is like there's n things. You go up to there's the state fair and there's these n prizes and you won a prize and you only get to pick one. And how many ways to do that? You could have picked prize number 1 or you could have picked prize number 2, right? But like the nth prize, so there's n ways to do this. Choosing one thing out of a list of n things. One of the things I want you to think about actively, so a little task for later, for at home, is fix. And this is just sort of like a build-up of a thing we looked at yesterday. I want you to fix an n and fix so that it works out. Let's just fix a k that's less than or equal to n. And I want you to think about, because it's an important task for next week anyway, come up with similar sounding counting problems. Okay, with final answers. Well, I want you to come up with a counting problem where one of the questions has a final answer n plus k, another has final answer n times k, another has final answer n choose k. Or, either way this is written. And if you want, it's a little more challenging to do, and it doesn't appear quite as often, but if you could come up with a 4th counting question where the final answer is the number of k permutations, great. But like, try to see if you can. I want you to think about actively sorting out when the sum rule, when the product rule applies versus when you have to choose k things out of n things. And I can say what I need to about this until I'm blue in the face. And I did not ask questions like this last semester, but I want you to think about these things, and you should look at what the requirements for the sum rule are, the product rule, and what combinations and permutations mean. And do a thing like, sorry to scroll up for a moment, but do a thing like this, right? Think about, like, let me box this in red here, right? Think about creating that connection, this correspondence, right? Like, if you can think about those kinds of things, and it's hard to do it first, but like the more you do that, I need. It's one thing to try to memorize or whatever when the sum rule versus the product rule applies. I want you to feel that intuitively, and you've got to practice counting questions, yes, but you also should try counting questions in reverse. It's just like everything else in math, right? We do integrals after derivatives. It's good to understand things in reverse as well. So it's one thing to come up with, it's one thing to look at counting questions that I provide, say, in upcoming homework, and for you to answer the counting question, and that's good to do, but it's also good for you to, I want you to actively think about reversing that process. Think about how you could come up with a question and try to trick yourself. And not, you know what I mean? Like similar sounding. The point is, a lot of the times the questions do sound similar. So I want you to think about which thing applies. Okay. So yeah, the comment that comes up next in my notes is the one so n choose r. This is also called a binomial coefficient. So that it's yet another name for this thing. So it's the number of combinations. It can be called n choose r. This is the moment in my PDF where I was going to introduce the LaTeX for it. But why? I think the thing we need to do is talk about why is this called a binomial coefficient, which just seems strange. And first of all, well, it's because of this. So I'd like to consider the binomial x plus y. Right? Binomial means two things added together. Okay. Then we're going to look at powers of this. So in x plus y quantity squared, right? If you FOIL this out, if you expand this out, every term has degree 2. Right? So, I mean, if you write it out and collect like terms as an x squared plus xy plus y squared. So by degree 2, I mean like even the xy right there, it's the power of x is 1, the power of y is 1, and when you add those exponents together, the overall total exponent is a 2. So the degree or the power is 2. In x plus y quantity to the third power, every term has degree 3. And of course this goes on, right? Like in x plus y to the fourth, when you expand it out, every term has degree 4. What I want to do to really dig into what's this connection between this number of r combinations or number of k combinations and this binomials business is I want to talk about the following question. It's a hard question, so we're going to ask the question and then look at a warm-up question in a moment. So after expanding x plus y quantity raised to the 5th power. So if we FOIL this out, if we expand this out, so after expanding this, but before collecting like terms, how many x squared y cubed terms are there? First of all, just from the discussion just a moment ago at the bottom of the last page, once you expand out, every term should be a degree 5, right? So that when you add up the exponent for x and the exponent for y, you should always get a 5. But so like for instance, we should expect terms that look like x squared y cubed, x squared times y cubed. But how many of them are there going to be overall? Well, I want to answer this question, but actually the fact that this is x plus y times x plus y plus the fact that it's the same thing over and over actually kind of makes it harder to see what's going on. So we're going to look at this believe it or not, this analogy question or this warm-up that actually makes it a little easier to spot what's going on. So I'm going to just choose different letters intentionally. So a plus b times c plus d times e plus f times g plus h times I plus j. So if you expand this out, and you can be methodical about it or whatever, but like one of the terms you're going to get is when you use the firsts out of each of these. So, right, so a times c times e times g times I is one of the terms. But then another term is instead of using the I, if you use here instead of the I, you use the j instead. So a times c times e times g times j instead of the I, right? And so on and so forth. And eventually, at some point, you're going to get one of the terms to be a times c times f times h times j, right? And there's more terms, but like I just want to make sure we're clear that you would get an a times c times f times h times j, because that'd be picking the a here and then the c amongst the c or the d, and then the f and then the h and then the j, right? The way you get a term when you expand it all out is you got to choose one of those, in each set of parentheses, it's one letter or the other. So how is this applicable? Well, now let's go back to x plus y quantity raised to the fifth power. So xy, x plus y times x plus y times x plus y. And the point is, if you choose like the first of each of these, the x each time, then you're going to get a term that looks like this, right? X times x times x times x times x. I'm intentionally writing analogous terms here, like obtained in the same way. If you, instead of choosing this x, you choose that y, where the second arrow is, just like we got this term here, you should be getting an x times x times x times x times y. And eventually, you'll get, just as was done over here, and I'll highlight in red in the same way, x times y times y times y. Right? So eventually you'll get x times y times y times y. And that x times y times y times y, that's one of those x squared y cubed terms. Right? So we're going to count this term. To answer this question over here, how many x squared y cubed terms are there? This is one of them, so we'll count it. Don't count these terms. Don't count x. We're not counting that term right now, but we're gonna count this term. And eventually, like somewhere hidden, either in the dots here or there, I didn't write them all out due to lack of time. But eventually, there's also going to be a y times x times y times x term. So where does that come from? So where does this blue thing come from? It comes from picking the y in the first x plus y, and then picking the x in the next binomial, and then choosing the y, and then choosing the y, and then picking the x, for example, right? And that's another x squared y cubed. So what I want to do is talk about how can we, like, instead of writing all this out, how can we account for all of these? How do we count? How can we account for all of the x squared y cubed terms? Well, I would like to think of it this way, okay? Think of it like there's 5 locations. So it's like, a little game of hangman, 1, 2, 3, 4, 5. And what we need to do is we need to choose any 3 of the 5 locations to be y's. And the rest are automatically going to be x's. Will just be x's, no more choices. So choose, out of these 3 locations, choose 5 of them, right? So this is there's 5 prizes, and now you get to choose 3 of them, right? So this is the number of ways to do this. This is 5, choose 3. So just to, I mean, you may want to write it all out once just to double check, but just to give another quick example, and then we can do a little pattern recognition and call it a theorem. So x plus y raised to the 10th. In this, how many terms are this kind? X to the 4th times y to the 6th. Again, this is same language as earlier. If you expand but you don't collect like terms yet. So then the point is over here, of the 10 factors, it says 8 in my notes. I should fix that. Of the 10 factors, these x plus y, you have to choose 6 of them to provide a y, and then the rest will automatically be x's, right? So think of this like these 10 locations again, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of 10 locations. Choose 6 to be y's. So in total, there's going to be 10 choose 6 ways of doing. There's 10 choose 6 ways of picking of these locations, picking 6 of them to be y's, and the rest will automatically have to be x's. And all the different positional ways of doing this end up creating all of the x to the 4th, y to the 6th terms. So more generally, right? So in x plus y to the nth, the number of x to the n minus j times y to the jth terms is n choose j. So do you always have to choose the bigger factor? Good question. Choosing x over y, choosing y over x? No, it doesn't matter. I've just been choosing y for the consistency. This is a really good question. You can choose either one. I've just been choosing the exponent of y as the number to put as, I don't know what to call that, the denominator, like with the 6 I circled, only because it's going to lead into the theorem and just match the notation. But either way is okay, because actually, sorry to scroll, where was it? Back here, yeah, this thingy. N choose r is the same as n choose n minus r. So the point is, I chose over here 5, I wrote it as 5 choose 3. This number is actually equal to 5 choose 2. So does that address it? You could have picked the exponent of the x. Same deal here. I wanted to keep it as 10 choose 6. You could have, this is equal to 10 choose 4. But I just picked the exponent of the y because it's going to notationally be consistent with the theorem I'm going to present in just a moment. That's all. So this is how many terms you have, n choose j of them, before collecting like terms. But let's say now you collect like terms. Collect like terms. Right? So you collect like terms, then you end up with a theorem called the oh my goodness. Let's try this again. Binomial theorem. This is a funky theorem that it actually works out so nicely is for any reals x and y, and we've just been, and for all n greater than equal to 0 integer, n greater than or equal to 0 integer, the following ends up being true. So x plus y raised to the nth power ends up equaling the sum j going from 0 to n of n choose j times x to the n minus j times y to the jth. All that's going on here is you're taking the number of terms there are and the coefficient in front of every single one of these is a 1. And so when you collect like terms, you're just adding together a bunch of 1s, right? So So the explanation of y here, all the coefficients were 1s. The coefficients were 1s before collecting like terms. So after collecting like terms, what's the coefficient? It's just the number of terms, if all the coefficients were 1 before. So as a brief example of this theorem at play, if you look at x plus y raised to the 5th power, and just follow what the sigma notation says this is. So I'm just going to write this out not in sigma notation. I'm just going to write this out for you. It's 5 choose 0, x to the 5 minus 0. Let's not write that. X to the 5, y to the 0th, plus 5 choose 1, x to the 4, y to the 1, plus 5 choose 2, x to the 3, y to the 2, plus 5 choose 3, x to the 2, y to the 3, plus 5 choose 4, x to the 1, y to the 4th, and then finally 5 choose 5, x to the 0th, y to the 5th. Okay, so that's an entire expansion. Like that's like literally, if you foiled it out, and maybe you want to try it, this is what you'll get. It's just I didn't simplify any of the binomial coefficients, but we could address the same idea in a much bigger question. What is the coefficient of x to the 75th, y to the 25th in x plus y raised to the 100th power? Now I don't want to write out this thingy, all of its terms, because over here, take a look. In the one that we just did up here, we raised to the 5th power and there were a total of 6 terms written out. I don't want to write out a total of 101 terms here, but we can just talk about the specific term that we need to here, and the coefficient that we're looking for, the coefficient here is 100 choose 25. At least that's what the formula here would suggest that we have. That's this circled here. That's that number. If you prefer, so that's the answer consistent to the theorem that was just presented, but also we could have said equal to 100 choose 100 minus 25. So in other words, 100 choose 75. So it's either about, the point is, why is it this number again? Just as a clarification of what was going on in the setup of this theorem, it's there's 100 locations. You're either choose, so 100 letter word for hangman, right? You have to choose the spots of the 25 y's, or you have to choose the locations of the 75 x's. And as soon as you choose where the 25 y's are, then where the x's are is automatic, for example. So, there's one last set of things I'm going to do, and I'm going to just copy, paste this thingy, just so we have reference of it. Okay, so the last things I want to note are these corollaries. I think we've talked about the word before, but as a reminder, a corollary is a theorem where the proof is really short, based on work you've already done. And of course, the work is the theorem we just have up there. So this corollary is for all n, a non-negative integer. The sum, k goes from 0 to n of n choose k is equal to 2 to the nth power. So what's the proof? Well, something related to the for all. I'm going to leave that to you. But the whole point is, all you have to do is in this statement up here in this blue box, which we already know to be true, let x equal 1 and y equal 1. Now this statement over here in this box was true for all reals x and y. So we're just using the fact that 1 is a real and plugging that in for x and for y. And look, the left side, 1 plus 1 quantity raised to the nth, that's 2 to the n. The other side, this other side, right, it's if you plug in 1 for the x's and y's, and this part circled here, that's just 1 raised to powers, so that's just 1 times whatever, and that drops out. So you're left with the sum j going from 0 to n of n choose j, and that's the same as the sum k going from 0 of n choose k. You're just switching what letter is the index. As a second corollary, for all n positive integer, and this is just out of some technicality that n equals 0 isn't allowed for this one, but let's not worry about that right now. The sum k equals 0 to n of n choose k times -1 to the kth power is equal to 0. So going back to the theorem up at here, the binomial theorem stated up here, what's a proof of this? Again, something related to the for all, but the key thing here is you just got to plug in x equals 1 and y equals -1. See, when you do that, then x plus y is 0, right? And 0 raised to the nth, so that you get a 0. That explains the right side. And then on the other side, well, you still have x is equal to 1, so 1 raised to whatever power, that part's going to be 1 anyway. And so all you end up with, this part's gone, and so then this here is what's right there, once you replace the y with a -1. Okay, I was going to say something about Pascal's triangle, but I just ran out of time, so we'll maybe make that comment tomorrow or just have you read it at some point, but I should call it with that.